Well, how's everybody doing out there? Well, welcome to day 25 of Corona Online School. So, we're moving into the final unit of the semester, and so this is all about decimals and the real number system. So, this actually kind of builds on everything that we've talked about up to this point and kind of combines all the number systems that we've learned into kind of this one giant number system called the real number systems. So before I get into that, I just wanted to say, congrats on the exam. So the ones I've graded so far look really, 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 really good. So you guys did a great job with the fractions. So that can be a tough, tricky subject for people. So I'm very proud of how hard you guys worked and the good models and things like that you guys put into it. So nicely done. All right, so let's finish off this unit. Well, not today, but let's get ready to finish off the last unit of the semester. So, chapter 7's it for us. So, just to kind of rehash what we've talked about. So, remember, we started off the semester with our natural numbers or the counting numbers. From there, we threw 0 into the mix. That gave us our whole numbers. From there, we threw in all the negatives. That gave us the integers. Then from there, we threw in all the fractions. So in this case, what we want to do is kind of use this graphic organizer. Let me turn it the other way real quick. Oops. So we can see the organizer better. Let me try to flip this thing around. Oh, come on. What are you doing? There we go. So we can see the whole thing. So the goal is what we want to do is kind of fill this guy in. And so, and if you remember these sets, so what we've got, this is just a big set, but instead of using circles, I used kind of squarey, rectangular looking things. So remember, when you have sets inside of sets, that means their subsets are contained inside of them. So like in this case, our inner set here is going to be our natural numbers. It's kind of the smallest of all the sets, and it's contained in all these other numbers. Then the next biggest number would be our whole numbers in this case. And then inside the whole numbers live inside the integers. And then finally, the rational numbers live out here. And so the idea is this big rectangle makes up all the real numbers. So the real numbers consist of all these guys. And the notation for real numbers is kind of this little Blackboard R is what it's called, or something like that. So the question is, what is this thing over here? What's this thing to the right? What lives in there? Because it seems like we've got pretty much most of the numbers right over here on the left. So what things don't fall into the left? Well, these are going to be your oddball numbers, things that can't be written as fractions and stuff like that. So things like pi, for example, would live over there. Like if you've heard of the number e, like 2.71828, so that would fall over there. Things like square root of 2, square root of 3, cube root of 7, anything with a radical that can't be simplified would live over there. So this is actually what's called our irrational numbers, the things that are over on this side. And so they're kind of interesting, and I talk about them a little down here because notice I didn't give the irrational numbers any kind of symbol like I did all these other ones. So sometimes you will see it written as a symbol, and I wrote it down here in the book, or in the notes, as R kind of backslash Q, which basically means it's the real numbers minus the rational numbers, which is pretty much what this set is actually showing us. So if this real numbers are the whole entire square, and I get rid of all this stuff on the left, then the only thing that's going to be left is going to be the irrationals. But one of the reasons that they don't get their own symbol, like all these other ones, all these other number systems you can do arithmetic in. And arithmetic kind of makes sense, except for the natural. Well, the whole natural numbers, technically, you can't really do arithmetic either. But you can add, you can't subtract or anything like that. But the irrationals are not closed. So if you remember, we talked about things being closed under addition or closed under multiplication. Well, the irrationals, that's not true. Because, for example, what if I took these two numbers, 1 over pi and pi over 2, And I said, what happens if I multiply these two guys together? So notice I end up getting 1/2 as my answer, which is pretty clear because the pi's are just going to cancel out. But 1/2 lives over here in the q's. So even though 1 over pi and pi over 2 are both things that live on the irrational side, when I multiply them together, they don't land inside the set. So that's there's kind of an example, because I talked about being closed and pretty much everything is closed. So this gives you a nice example to demonstrate that the closure property doesn't hold with the irrationals. So that means it's not going to be a nice set like the rational numbers or the integers and things like that. So we can't perform addition. So the only way we can perform addition on irrational numbers is by having the rational numbers with us. We need to have all those real numbers to be able to do that in this case. So anyway, this is my long-winded talk about it. So if you want to read a little bit about that stuff, that's kind of what I was getting at up there. So again, just to summarize, what's our real number system? So again, we've got our natural numbers, which I'd wrote above. So again, it's going to be our counting numbers, our whole numbers, which is 0 plus the counting numbers, our integers, our rational numbers, again, which is going to be that like m over n, where m's an element of z and n's an element of z minus q in this case. And then the irrational numbers, again, are going to be all of our oddball things. So again, there's really no nice, easy way to write it other than just the reals minus q in this case. So, all right. So next couple are practice ones. So I thought I'd have you guys work on these. These can be a little bit tricky. So it's possible that these might be the exit ticket just to make sure you know what's going on. But it kind of is making you think about how these sets are actually related and things like that, in terms of our diagram above. And then practice 3 is going through and just kind of writing yes or no in each of the columns as to where these guys live. So in this case, like the number 8, for example, and you can't have yes in more than one column because, again, these sets are contained in each other. So 8's a counting number, so that would be a yes. It's a whole number, so it's a yes. It's an integer, so it's a yes. It's a rational, so it's not irrational, but it's a real. So basically the thing to remember is the first yes you come to, like if it's a one of these natural whole integer rational numbers, then it's going to be yes every way up to the irrational at that point. So if it's a whole number, it's also an integer, it's also a rational. If it's an integer, it's also a rational. So almost all of these are real. There is one non-real one in there, so hopefully you guys can pick it out. So I gave you a little warning about that. So work on that practice 3. And then when you're done, come on back and we'll talk about the place value system for decimals. So we've done it for whole numbers, so now we want to expand this into the decimals in this case. All right, so hopefully everybody did a good job on the true falses and being able to identify the different numbers and stuff like that and what categories they fell into. So in this case, we want to talk about the decimal place value system, which we haven't talked about yet. So basically what we've looked at is everything to the left of the units. And so these should all look familiar. So we've got our units, our tens, our hundreds, and our thousands. And so we've got our, kind of tens version, and then we've got our exponent version. And so now we want to look to the right and notice there's nice symmetry around the units position. So in this case, the first one to the right of the units is the tenths, so with the THS at the end. And so it kind of matches with the tens. So in this case, this is going to be 1 over 10, or as a decimal, 0.1, and then 10 to the minus 1. We've got our hundredths, which again is kind of matched up with our hundreds. So it's 1 over 100, 0.01, 10 to the negative 2. And then finally our thousandths is kind of paired up with our thousands. So 1 over 1,000, 0.001, 10 to the negative 3. And then again, if we're moving around, I wrote divisions here, but if we turn the arrows the other way, like we could go from one to the other by just multiplying each spot by 10 is the idea. So if I want to go from the thousands to the hundreds, then I'm basically just dividing by 10, or essentially I'm just moving the decimal point one way. Same thing if I go from the thousands to the tens, I'm taking a big number and making it smaller. So that way I'd end up moving the decimal point around. So a lot of this stuff you can do by just moving, if you're multiplying by 10 or dividing by 10, you can do a lot by just moving decimals rather than actually having to do the whole division out. All right, so practice 4 is talking about the density of rational numbers related to decimals. So we did this with fractions. So now I want you to do the same thing with decimals. So just follow the rules on there, see what it tells you to do. And then when you're done, come on back and we'll do some practice problems here. All right, so the goal at this point is what we want to do is we want to write this decimal number in expanded exponential form. So we've done this for whole numbers. We haven't done it for decimals yet, but it's the same idea. So what I'm going to do first is kind of break this apart into this form first. All right, and so notice there was a 0 between the 1 and the 4, so I didn't put it in there. If you want to put it in there, you're more than welcome to, but I just kind of left it out because you can. So now I want to turn these from the kind of the decimal form into the exponential form. So 600 is going to be the same thing as 6 times 10 squared. 50 is going to be the same thing as 5 times 10 to the 1. 3 is the same thing as 3 times 10 to the 0. Plus 0.1 is going to be the same thing as 1 times 10 to the negative 1. And then plus 0.004 is going to be 4 times 10 to the negative 3. So notice I skipped negative 2 because there was a 0 in that spot. But if you wanted to, you could have written plus 0 times 10 to the negative 2. And that would have been totally fine also. So this is what we're looking for when we're trying to get expanded exponential form in this case. All right, so you work on practice 5 real quick. And then when you're done, unpause the video. And then we'll talk about how to multiply or divide by a power of 10. All right, so in this case, we could just straight multiply and everything would be totally fine. But the idea is if we can do a little shortcut or a little trick, it would make life a little bit easier than having to actually go through the multiplication. So again, the idea is if we're multiplying by something, by a number, then what we're going to do is we're going to move the decimal to the right to make it a bigger number. And how many decimal places do we move it by? Well, it's basically just however many zeros there are in this case. So in this case, we're multiplying by 100. So that means we'd want to move 2 decimal places because we've got 2 zeros. So this would look like 4562.3. And of course, you can multiply it out and you'll get the exact same answer. But it's nice if you can learn some of these little shortcuts and stuff like that to help with the calculations, so that way you may not have to use a calculator and stuff like that. All right, so in this case, when we're dividing by something that's 100, we're going to move the decimal to the left because, again, we're trying to make it a smaller number. Oops. And so again, how many places to the left do I move it? Again, it's all based on the zero. So since I've got 2 zeros in 100, starting at the decimal, I'm going to move 2 places back. So that's going to give me 87.3245, which again gives me a nice smaller number. All right. So go ahead, do practice 6, which is having you guys do the exact same thing here. And then when you're done, unpause it. And what we want to do is talk a little bit about converting fractions to decimals and then decimals back into fractions. All right. So hopefully everybody did a good job with multiplying and dividing by powers of 10. So in this case, what we want to do is we want to start off with a fraction and we want to turn this into a decimal. So what we do is we just do regular old long division on this, and then, but we're going to have to add some zeros in order to be able to actually finish this off in this case. So what we want to do is put our 75 on the outside. Actually, let me give myself some more room just to make sure. And then 14 here. And then what I'm going to do is I'm going to put some zeros on here. So I don't know how many I'm going to need, so I'm just going to put 4 on there. I can always add more if I need to, or if I add too many, I can erase some. So it doesn't matter. And so we're going to talk about dividing decimals in the next section, but hopefully you remember enough at this point that what you need to do is just move the decimal straight up. So in this case, like so, and then once you place that decimal, then it's just like dividing integers, whole numbers, all that kind of stuff. So just place the decimal right away, and then the rest of it's just regular old division. So in this case, I want to see how many times does 75 go into 140. So I think that's just one time. So in this case, we'll turn this into a 13, carry the 1, so 5, so 65, and then bring down our 0. And then 75 goes into 650, 8's 56, 9 is 63. So let's try 8, see what happens here. So 75 times 8, 0, 4, 56, 600. So bring down our 50. And then bring down another 0. So 75 goes into 500. Let's see, 7's 49. I think that's going to be too much. Let's try 6. So it says 30, 42, 45. Oh, I forgot to put my 6 up there. So at this point, we could keep going, but since we had 500 the last time, I'm going to get 500 again. What this means is this is just going to keep repeating over and over and over and over and over again. So this is just going to be a bunch of 6s. So what we do when we have repeating decimals is we'd end up kind of like just putting a line over the last repeating number and just kind of leave it at that. But that's what we're looking for in this case, to kind of show, like, just go until we can either it ends, or hopefully we can kind of recognize that it's repeating, and then we'll be done. All right, so again, pause the video at this point. You guys actually go ahead and work on practice 7, and then when you're done, we're going to talk about is terminating decimals and things like that. So all right, so if we look at the terminating decimals and rational number, so if you forget this, it's not that big of a deal because you can just kind of divide them out and see what happens. But this is kind of cool. So terminating decimal means it's going to actually end. So it won't go on and on and on and on forever. So like the one I had, it was going to keep dividing and stuff like that. And so it turns out that if you've got your fraction in reduced terms, so in this case, 14 over 75 is 2 times 7, and then 3 times 5 times 5. So nothing cancels out. So that's what we mean by simplest form. Then if your b, the bottom number, contains only 2's and 5's in its prime factorization, then a and b can always be written as a terminating decimal. So that means it's going to actually stop. So notice mine didn't stop. And the reason it didn't stop is because it had that 3 in there. So if it had just had those 5's, this thing would have ended and everything would have been totally fine, which is kind of neat. So it's kind of neat to be able to look ahead of time and say, oh, okay, well, this should end or this won't end, just by looking at the denominator and trying to figure out what kind of prime factors are in the denominator. All right, so let's take a look at going the opposite way. How do we convert a terminating decimal into a fraction in this case? So what we want to do is actually just kind of use the fact that, just turn it into a decimal by using our, 10 to the, 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, whatever we need to do. So in this case, since I'm so I've got the tenths, the hundredths, the thousands, the 10,000ths place. So my 4 is in the 10,000ths place. So to write this as a fraction, what I want to do is take 45864, put it on top, and then write it over the position. So in this case, over 10,000. Look at that. Easy as pie. I'm done, right? So hopefully someone's screaming out in the audience, no, you're not done, because this isn't in simplified form yet. So we do have, it is in a fraction, but the goal is we always want our fraction to be in simplified form. So we still have to do a little bit of work. So again, this is just like we've been doing. So like first thing I would notice is both the top and bottom are even. So I would just take the top and the bottom and divide them both by 2 in this case. So the bottom's easier because it's going to be just 5,000. So if I divide the top, I'm going to get 2 goes into 5864 one time. 2 goes into 18 9 times. Leaves a 0. Bring the 6 down. 2 goes into 6 3 times. Another 0. Bring down the 4 2 times. So now they're both even again. So let's do the same thing again. So the bottom again is pretty easy. It's just 2,500. But now I want to take 1932, divide it by 2. So 9 times 2 is 18. 2 goes into 13 6 times. 2 goes into 12 6 times. So they're still even. Let's try this again. So 2,500 divided by 2 is 1,250. So 2 goes into 966 4 times. And then 8 times. And then 3 times. So in this case, they're not even. So we can't go any further. And I think at this point, we're actually done. So because the bottom one can only be divided by even numbers or 5. And so the top number being odd, looks like we've actually run out of stuff. So it looks like 0.5864 as a decimal is the same thing as 483 over 1250. All right. So again, I got a couple for you guys to practice here. So work on practice 8, see what you come up with. And then when you're done, then we'll talk about rational and repeating decimal or periodic decimals, or what's the same thing as repeating decimals, which is that first example I showed you above. All right. So again, we've got a nice little theorem that gives us a little heads up as to whether something's going to be repeating or not repeating. So every repeating decimal, that's represented by a over b, again, it has to be in simple form, contains factors other than 2 and 5. So again, problem with the one I had up here, it had that factor of 3 in there. And so just because of that, it forced it to be a repeating decimal as opposed to a terminating decimal in that case. So again, if you don't remember it, it's not that big of a deal, but it is kind of cool that there's actual rules that you could look at ahead of time to determine whether you're going to end up, having a repeating or a non-repeating decimal. All right, so let's take a look at example 5 here. So example 5 is a little bit trickier, because in this case, what we're trying to do is we're trying to convert a repeating decimal into a fraction. So we know these actually come from fractions. I mean, because like we proved in example 3 that repeating decimal came from a fraction. So the question is, how do I kind of work backwards and turn this into a fraction? So it was easy enough to do when we had our terminating decimal, because we could just write it over 10,000, write it over 1,000. But in this case, 0.6 repeating is going to go on and on and on and on and on forever. And so the problem is, I can't just say, I can't raise it to the 10,000 because, it goes out to the 100,000th place, or I can't raise it to the 1,000,000th because it goes out to the 1,000,000th, the billionth place and stuff like that. So I've got to have a way that I can solve this to do it. So what we have to do is kind of a little algebra and play around with it a little bit. So the first thing we do is we let x equal this repeating decimal, so 0.666666, just a bunch of times. And then what we're going to do is a little trick to this. So what we want to do is take that first equation and multiply it by 10. So when I multiply this by 10, this next, the left-hand side just becomes 10x. But notice what happens to the right-hand side. So since I multiplied it by 10, I'm going to move the decimal point one place to the right. So in this case, I'm going to get 6.66666 a bunch of times. And so now what I want to do is actually subtract these two equations from each other. So let me write minus x 0.66666 underneath. So the left-hand side's nice and easy. So 10x minus 1x is the same thing as 9x. But what happens on the right-hand side when I subtract that? Well, hopefully a bunch of people are screaming out, well, all the decimals disappear. Yeah, exactly, because over here, everything to the right of that decimal is exactly the same. So they're just going to cancel out. So in the end, all that's left on the right-hand side is just plain old 6. And so now if I divide this by 9, I see that x is the same thing as, whoops, I'm jumping ahead, sorry. 6 over 9, which in reduced forms would be 2/3. And you may recognize that decimal as 2/3. So some of these may look familiar to you and stuff like that. So again, that's kind of a cool little trick that you can do with algebra to turn a repeating decimal into an actual fraction. All right, so let's look at question B here, because this one requires a slightly different trick, but the same idea. So in this case, again, what we've got is if I write this out, it's going to be 4.15. It's not 0.15. 4151515151515 forever and ever and ever. So again, we start off exactly the same way we did before. So let's let x equal 4.151515, and I'll just kind of stop there. So now in this case, what if we tried to do the same trick? What if I said, okay, well, let's multiply both sides by 10, see what happens. So if I multiply this by 10, again, this is just going to move the decimal place one to the right. And then if I subtract this by x, what do you notice? Well, hopefully nothing good, because if I've got these lined up correctly, I've got the 5 over the 1 over the 5, and so when I subtract this, I'm going to get stuff still in the decimal, which is not really helping me at all. So multiplying this by 10 didn't really work in this case. So let's go back to the drawing board in this case. And the reason it didn't work, and it worked above, is because in this case, there was just one number 6. And so just by moving one place over made everything work. In this case, the problem is my repeated numbers, there's a pair of them. So moving by just one decimal spot, the decimal place isn't going to get me over enough to get the answer that I'm looking for. So in this case, I need to move it by 100, so that way I can move it 2 decimal places, so that way I can get the 1s and the 5s to line up. So in this case, let's multiply both sides of the top equation by 100. So now I move it 2 decimal places, so I end up with 415.151515 forever and ever and ever. So now let's subtract. So let's bring this other equation down below. Now we've got exactly what we were looking for on the right, because all these 1 5s are paired up and they're underneath each other. So in this case, these guys are going to cancel like we wanted. So 415 minus 4 would be 411. And then 100x minus 1x would be 99x. And then finally, divide both sides by 99. 411 over 99. All right. So that looks pretty good. So here's a couple for you guys to try. So I put a couple different varieties in there for you guys to work on. So if you get stuck or anything like that, just let me know. Otherwise, work on practice 9. And then when you're done, come on back and we'll look at some ordering decimals and finally done for the class. So a bunch of stuff today. So, all right. So ordering decimals turns out, hopefully you find it that it's a lot easier than ordering fractions, for example. And if you see down below, there are some decimals mixed with fractions. So the goal is to turn everything into a decimal first, and then kind of use that as a way to figure out which one's bigger and which one's smaller. The reason decimals, in my opinion, are probably easier to figure out which one's bigger or which one's smaller is because, again, we have our number system available to use, because we don't have much trouble figuring out which integer is bigger than another integer, because we just match them up by, like we look at the tens. If they're the same at the tens, we go out to the hundreds. If they're the same at the hundreds, we go out to the thousands. So the same thing's going to be true here, except now we'll have to start with the decimals and try to kind of work our way that way with them. So first thing you want to do, so with mine, I've got repeating decimals here. So what I'd want to do is write them not in repeating decimal form first. And I'm going to try to line them one on top of the other one, just so that way I can kind of look at the decimal places as I go along. So 4.15662 repeating is going to look like 4.15662, 662, 662. And 4.156 repeating is going to look like 4.15666666666. And again, these just keep going on and on and on forever. And so now what we're going to do is kind of start with the left and just go through until we can find the first place that these guys differ, so we can figure out which one's bigger and which one's smaller. So in the units position, they're both exactly the same. So at this point, we can't tell whether one's bigger or the other. In the tenths position, they're exactly the same. So again, we're no better off than we were before. In the hundredths position, again, they're both exactly the same. In the thousandths position, still exactly the same. 10,000ths position, still exactly the same. Finally, now that we're at the 100,000ths position, we see that we've got a 2 in the top number and a 6 in the bottom number. Since 2 is smaller than 6, then that means this top number has to be the smaller number, and the 4.156 repeating is going to be the bigger number. So in this case, if I were to write this out, I would say 4.15662 repeating is less than 4.156 repeating in this case. All right, so you guys are going to do the same thing. So you've got a bunch of different problems. Again, I'd recommend turning all the fractions into decimals, just so that way it's much, much easier to compare them all the same. And I'll be around all day if you have any questions or anything like that. So have fun with it and good luck.